Okay. So I think someone just now raised hand. Is it Vedant? If I saw the name correctly, do you have any question? You can go ahead.
No, sir, no questions.
Okay. Okay, great. So let me share my screen. Yeah, it's visible to everyone.
Yes, sir, it's visible.
Okay, great. Okay, so welcome to the first lecture of Fields and Webs. So today I'm going to give you some brief overview of the course, the grading policy, what we are going to study, uh, and also some ground rules that I would expect that you would stick to, and some brief overview of what is a field, what is a wave, because the name of the course is Fields and Webs, right? So I want to expose you at the very outset that what do we mean by field and what do we mean by wave, okay? So the grading policy, so first of all, I think you already know from your seniors that this course maintains a zero tolerance towards plagiarism or cheating in any of the grading components. So please don't do that, okay? I will have to report you to the academic section. I am usually strict in this aspect, okay? And it will be dealt as per the institute policy. So as far as the different grading components are concerned, the midsem will be a 25% of weightage, endsem 35%. There will be total 3 to 4 assignments, and probably they will be posted fortnightly or at an interval of 25 days, depending on the situation. Okay, and quiz, there will be total 3 quizzes, and all of them will be in class, and I'll announce them in prior. Okay, and it will be a 20% weightage. The grading is going to be relative. Okay, so usually the question papers in this course is not easy. Okay, so you have to read thoroughly, you have to attend classes. So I'm not going to force you to attend classes, but if you do so, then it will be beneficial for you. And the following is the penalty for late submission of the assignments. After the submission deadline is over, a penalty of 25% of the obtained marks will be imposed per day. Okay, so suppose if you are scoring 12 marks in some assignments, then each day, or suppose you are submitting the assignment one day late and you obtain 12, so you will be assigned 3 marks lesser. Okay, 2 days late, 6 marks lesser, like that, and 0 marks if you are submitting the assignments after 4th day. Okay, I'll only be flexible with the first assignment in this course. Okay, so this being a very first course of electromagnetics, and it's a pretty daunting subject, so keeping that in mind, and also given the COVID situation, the wave which we are all passing through right now, the first assignment will not have any late marking. Okay, so you can submit it probably a week late. Okay, so the deadline that I'll specify in the assignment will be a soft deadline, but the hard deadline will be 1 week. Okay, but please do not delay more than 1 week. Okay, for the first assignment, unless there's a good reason to do so. Okay, so some of the general instruction, all the quizzes and exams will be proctored. Okay, in case you aren't able to attend any of these because of maybe the power outage or internet outage, a viva will be taken in lieu of the particular grading component. Suppose you missed a quiz because your internet wasn't working, or you couldn't submit the question paper, or the answer script, or you had some power outages because of which your Wi-Fi stopped, then we'll have to take a viva in lieu of that. Okay, and this is a very general rule which is being followed in IIT Delhi too. Okay, so we will do that. Okay, but you can be assured that if you are facing any problem, there will be a substitute viva. Okay, So in case of any questions related to the topics taught in the class, just drop me an email, okay? If it is possible for me to answer the questions over email, I'll do so. If not, then we will set up an office hour and on a mutually convenient time, and we can discuss that. And whenever someone is having any question, I'll be broadcasting the office hour link to everyone. And any of you can, if you feel that the discussion will be beneficial for you, you can just pop in into the class and we will clear your doubts. And in case of any other questions, for example, anything related to tutorials or anything related to some links which is not working, your point of contact will be the TS, okay? Mr. Rana Kumar Jana and Mr. Tushar Agarwal. So both of them, they are there right now. These two are the assigned TS in the course. And if it remains unresolved, you can always write to me, okay? But I'll prefer first you approach them if it is not anything related to the topics which are being taught in the class, okay? Or if it is not a doubt. So if you have missed a grading component due to medical reasons, just email academic section directly with all your relevant documents, the prescriptions, the reports, etc. And please keep me in CC, okay? As soon as I get a direction from the academic section that you have submitted this and these are on a genuine ground, we would be happy to consider alternative exam for you, okay? So only for medical reason, if you are missing your grading component, for example, a quiz or a exam, then I'll take an alternate quiz and exam, not a viva, okay? But if you are missing it for power or internet outages, then we'll have to, take a viva for that. Okay? But in this particular case, if there are any medical ground or if you need to take care of your any family member in these trying times, we are flexible and we will have the alternate grading component ready for you once you provide the the documents to the academic section and keep me abreast, okay? So in general, the lectures are going to be recorded and shared with all of you. However, there's a catch. If during any of the semester, the attendance falls below 60% of the total class strength, okay, any day, the lecture won't be recorded. Or suppose you were joining, when you are joining the lecture, the attendance is above 60%, but after half an hour, you just log out and it falls below 60%. I'm sorry, I'll not be recording the lectures, okay? So it may seem to you that I'm being a little bit, strict in this respect, but there's a good reason to do so. So what I saw in some of the batches that I taught online, that the attendance fell very thin, okay? And most of the people who didn't attend classes, they even didn't knew at the end of the semester how to write a particular vector calculus notation. Forget about solving the equations. So if you just come to the class, if you just listen to it, you at least you will have some understanding of what is going on, okay? So please make sure that the attendance in the class is more than 60% of the class strength. And given that most of you are from Delhi, I don't think that it will be much of a problem when it comes to the internet problem, okay? So yeah, I hope that these are clear. So if you have any questions so far, you can please go ahead and ask me. Anyone, any question, please go ahead.
So there won't be any viva for assignment, quiz, or the mid-sem something like, right?
No. So the midsem, the assignments, the quizzes, they will be on pen and paper. Okay, you have to solve problems. You have to submit your answer script and all. But if you are missing it due to, for example, the power outage and internet outage, okay, then I'll take a viva. Okay.
Yes, sir.
Yeah, but you will not be deprived of the grading component altogether, right? So it's not like that you have missed it because of some internet outage or power outage, and I'll tell you no, you are missing the marks. No, it won't work that way. So you will be given an alternate chance to appear for a viva, and the same weightage will be given to that viva as it was in the mixed grading component. Okay.
So can you refer some textbook?
Yeah, it will come. It will come. No, the quizzes will not be a surprise quiz. It will be announced, but the thing is that it will be announced at least 1 week prior to the conduction of the quiz. But please prepare properly. Okay. Again, this being online setting for obvious reasons, the question paper is going to be a little bit on the tougher side. So if you listen to the lectures, if you apply your mind, there is no N-1, Rakesh. But yeah, if you are missing one quiz because of some genuine reason, then, for example, if you are missing it because of medical reason, then there will be an alternate quiz that will be sent out to you separately. Okay, and that will be proctored too. And if you are missing it because of non-medical reasons such as power outage or internet outage, then there will be a viva. But there won't be a N-1. If there is no genuine reason for which you have missed the quiz, then sorry, I mean, there won't be any alternate this thing. Yeah, so the midsem will, the midsem or the quizzes and the assignments, they will contain a mix of MCQ and some problems or some theorems that you need to prove. So it will be a mix of everything. So it's not going to be, particularly MCQ or particularly descriptive questions or particularly some proof or some problems. It can be a mixture of any of them, and the ratio will vary depending on the situation. Okay. Okay. Any other question you might have?
Sir, the books which you will
Sorry,
be...
the book, right? Yeah. So I'll come to that. I'll come to that in a bit. Okay. So let me go forward with the course outline and the reference books and what we have coming in the next few weeks or few months of the lecture. So the course contains 5 parts. It's the review of vector calculus. Okay, so where I'll be brushing up the concepts for the curl, gradient, divergence, their physical interpretation, and line integral, surface integral, and volume integral. All these things. Okay, and then there will be electrostatics. Okay, and then there will be magnetostatics, and after that there's going to be electrodynamics. Okay, so now what is the difference between electrostatics and electrodynamics? Can any of you give me an idea of that?
Dynamic is continuously changing, and electrostatic is not changing so much.
Yeah.
One deals with charges at rest, other deals with moving charges.
Well, I won't say that whether it's a moving charge or a charge at rest, because there can be situations where the charges are moving with constant velocity. Okay, and if that is the situation, then still it will be treated as statics. Okay, for example, if you have a constant current flowing through a wire, okay, you have probably studied the Biot-Savart's law in your class 2, right? You will find there that the magnetic field that this DC current creates, it's a static magnetic field. The magnetic field doesn't vary with time. Okay, so even though the charge is moving with a constant velocity, it can be a static situation. Okay, so you are basically getting magnetostatics from there. So dynamics means, yeah, when the field, okay, either the electric field or the magnetic field, okay, they're changing with time. Okay, whenever there's a time variation involved in the fields or in the potential, then you call that electrodynamics. Okay, otherwise you either call it electrostatics or magnetostatics, depending on whether you are dealing with electric field or magnetic field. Okay, so it all has to do with the time variation of the field and the potential. Okay, not the velocity of the charge. But yeah, if the charge is accelerated, I'm going to show you that whenever you cause an acceleration in the charge, then an electromagnetic wave is radiated. Okay. So after studying electrodynamics, we will come to the proper study of the electromagnetic waves, the wave equations, reflections of electromagnetic waves from certain surfaces. Okay. Mostly waves that are propagating in the free space, okay, or unbounded dielectric medium. For example, you have a very, very long a piece of glass slab and the wave is propagating in that, or you have just air, a wave is being radiated from an antenna and it's propagating. So how would the propagating wave look like? What would be the characteristics, so on and so forth? Okay, so this is electromagnetic waves in unbounded medium. And then towards the end of the course, we'll face a scenario where the wave will be guided. Okay, so what do we mean by guided wave? Guided wave, as the name suggests, that from the source to the destination, the energy of the wave is not allowed to spread throughout the medium. Okay, rather it's kept confined in a certain region of the medium and guided towards the destination. Okay, so these type of waves are called the guided waves, and transmission line is something that deals with the guided wave. So to give you some example of the transmission line, you will see that from the dish TV, there's a coaxial cable which is running to the back of your TV. Okay, so that's the or to the back of your set-top box, right? So that's one example of transmission line. So coaxial cable is one type of transmission line. There are several other types of transmission line, okay, that we will encounter, but the basic mechanism is the same. What it does is that coaxial cable has got an inner core and an outer core, right? If you cut down the cable, then you will see that there's an inner core and there's an outer core, right? So the energy of the electromagnetic wave, it remains confined within the inner and the outer core. It doesn't come outside the cable, right? And it gets guided to the set-top box from your TV antenna. Okay, so this is one example of transmission line, but what is the theory of propagation of electromagnetic wave? How the current and voltage they appears, okay, from the basic electromagnetics. All these things, they will appear in the study of the transmission line, okay. So the books that we are going to follow is David J. Griffith's Introduction to Electrodynamics. You can just write to the library, and I believe they have the soft copy access to this book, and they will arrange for the access. Okay, and then the second book is a very nice one, a very nicely written book by the famous physicist Richard Feynman. It's called the Feynman Lectures on Physics, and you will need to study volume 2. This book is available in the Caltech library freely. Okay, so there's an online version of this book. So just type it up and go to the volume 2, and you can just dig up the chapter on electromagnetics and start studying it. Okay, this is a very nice read. Okay, and in fact, if you are in general interested in any other aspect of physics, there is volume 1 and 3. You can go through them as well. Okay, but this is a very, very nice resource, and it will make your understanding, crystal clear on a subject. So for some of the topics that I'll mention on the go and the transmission line part, you will mostly study Matthew Enosadiku, Elements of Electromagnetics. Again, this book is there in the library. You can just drop an email to the library and get access to the book. Okay, but the Enosadicu's book will be useful mostly in the transmission line and very little in some other topics. Mostly we'll be following Griffiths, and for your understanding, you can study Feynman's Lectures on Physics. Okay, so all these will be posted to the. In fact, these slides will be posted to the Google Classroom, so you will have the names handy. Okay. All right. So if you have any question, any doubt till this point, anything you want to you want to know or you want to suggest in terms of conduction of the course and all, you can go ahead. So any question?
Sir, can you make your screen in the landscape mode?
Okay, I can do that, but the problem will be there when I actually start, so let's see how it works out. Is this okay with everyone?
Yes, sir.
Yes, sir.
So let's see if there will be any problem when I write down something on the notepad to explain to you. Okay. So when it comes to the presentation, it's very easy. But yeah, so then I'll have access to very limited number of lines when it's in landscape. But let's see how it works out. Okay. All right. So any other thing?
Sir, could you share the classroom code?
It's already shared in the Google Doc. That has been shared with you from the academic section. Okay.
Sir, can we have N-1 policy? Like it's help a lot many time in starting of the course.
Sorry, what is that?
N-1 policy, best out of 4 or best out of 3
No,
quiz.
the problem is this. Okay, the problem is this. I mean, greater the number of the quizzes and assignments, greater is the pressure on the student. Okay, plus I'm virtually giving you, the N-1 thing already, because if you are missing anything for a genuine reason, then it will be there will be a alternate test just for you, not for the entire class. Okay. But we will see towards the end that if we see that the situation is grim, the scores are not too high, then we will go for N-1, but that is the last thing that I would like to do. So I am not committing to anything by saying this, that there could be a N-1. Mostly 99.99% you can be sure that it won't be. But if you are missing any component, then yeah. It will be taken care of by means of either Viva or alternative quiz or assignment. Okay. It will be individual. Assignments will be individual. So just let me open the in-call messages. Yeah, you can choose a book, as per your preference, but most of the materials I'll cover, they will be from Griffiths. Okay, but the same topics, yeah, they are available to any other book, not only the 3 books that I'm mentioning here, but in any other book. So if you feel that you need to read a topic from another book, so please go ahead. So, okay, so one of the question is that will the midsem or anything be open book or not? So it will be decided and announced to you prior to the particular exam. Okay, I mean in advance. Okay, at least 15 to 20 days before, if it is being made open book. But usually the downline is that. The downside is that if it is open book, the questions they have to be much more tougher. So many of you don't want that. So this is what I understood from the last 2 batches. Like if it is open book, some people like it and the others not, because the questions are on the tougher side. Okay. So, but yeah, if it is being made open book, it will be announced to you. Okay, any other question?
So can you show the books once again?
Yeah, sure. So this lecture slides and the recording will be posted to the classroom page, so you can always go back and have access to.
Sir, can you share the previous year grading versus percentage score in the course?
No. So why do you need that?
No, I mean we'll get an idea uh, on how much
So
we need to
I
work.
have never given that grades, okay? Because
Okay, sir.
it's always relative. The questions will be tough, you can be sure, okay? The questions is a little bit on the tougher side. So if you don't study, you will not score high. But as far as the grades are concerned, they are relative grading. So if you are suffering, then there's a high chance that the other students, they are also, facing the question paper as tough. So it never becomes easier for them, right? So since it's always relative grading, you end up getting a good grade anyways, right? But the only thing is that you have to study properly, because if someone is not finding the question paper tough, and if you find the question paper excessively tough, then that means that with the same course material, you probably missed something, or there was a lack of preparation before coming to the exam. So plug in all those holes, okay, and don't worry about the grades. That's the one advice from my side. Okay, but usually in a relative grading, you don't end up getting bad grades, because your preparation will be at par, or at least the average level uh, with respect to the class. Okay. Okay. So anything else? So yeah, if the attendance is below 60%, then if it's a slide, the slides will be shared. If it's not a slide, so if I'm doing board work, then I might have some class notes for you that will be shared. Okay, but the recorded lecture won't be shared. So please make sure that even if for some reason you are not being able to come to the class, the attendance stays above 60%. Just request your fellow students to be present. The reason is that, so the only reason I am doing is because of your own good. Okay, so I don't want you to be in a situation that at the end of the semester you write your end sem exam and you don't know how to write. For example, the curl sign, the gradient sign, the divergence sign. I mean, believe me, this happened. This happened many times. So this is a serious issue, and this was also discussed in the many of the meetings in the department. Okay, so these are some genuine issues. So I don't want you to be, in that kind of a situation. At least come to the class and you will learn. I can assure you, if you listen to the lecture, if you attend the class, you will learn something about the subject. Okay, there will be some very nice demos. So most of the people, they say that electromagnetics is very tough because you cannot see the waves and all. But I'll try my best from my side so that I can give you a good visualization of what is happening through many of the online demos that has been taught in other universities. Okay. So yeah, that's a good question, Vedant. So class average is 43 and two people managed to score somehow 95 plus. So the class average goes up. That's how relative grading works. Okay. So, you have to convince you have to annoy the fellow students so that they don't get enough time to study to score 95 plus. That's the only thing I can say. So either you study hard or don't allow them to study. Okay, so So usually you see the class average, it corresponds to either B neg or B. Okay, so if you are scoring average, then probably you'll get a B neg or B. Okay, mostly B, I think. So the line is not very, very clear. So sometimes it's B neg, sometimes it's B. So if you are scoring average, then it's going to be B or B neg. Anything above that, A plus, etc. Okay. All right. So now let's move forward. So, just when I switch on this, presentation, or when I'll be writing on the notepad, I won't be able to see the in-call messages. Okay, so whenever you are typing something in the chat box, I won't be able to see that. So just in case there are any important messages that needs to be addressed, instead of typing it up there, just just speak up and I'll be able to address that immediately. Okay. So for example, right now I'm not able to see the chat box. So yeah. So just speak up, All right. So first of all, I want to go by the name of the course. The name of the course is Fields and Waves. Okay. So how many of you can tell me what a wave is? So let me hear you up. That what do you mean by a wave? Okay. So you have seen water waves. You have encountered sound waves. Okay.
A disturbance.
Mm-hmm.
Like a disturbance in the physical space.
Okay. So what is the nature of the disturbance? That's a good answer. But what is the nature of the disturbance?
Periodic.
Okay. So that's something I'm going to address. That it doesn't have to be periodic. Okay. I'll explain to you how. So it doesn't have to be repetitive. But the question is, for example, in the sound wave, what is the disturbance? Right? So when you say that there is some disturbance, you have to tell what is the particular physical quantity that you would associate to the disturbance in case of sound wave. What is the physical quantity that you would associate with the water wave? Okay. So for example, when we talk about the sound wave, when you say disturbance, what is the corresponding physical quantity that changes? Disturbance means some change, right? So what's that?
Pressure.
Pressure.
Yeah, the pressure changes, right? And just to give you some example, right? That why it doesn't have to be repetitive. So if you are taking a tuning fork and if you are just hitting the tuning fork with a hammer, then a buzzing sound of a particular frequency will come out, right? So as long as the tuning fork is keeping on vibrating, it's a continuous wave. It's a continuous disturbance. It's a repetitive phenomenon. It's an oscillation that's going on. So the corresponding wave is periodic, right? But suppose you hit the tuning fork and then immediately hold it by your hand so that the vibration stops. But still a sound wave got emitted, right? So it was a very short-lived thing. So it was not a repetitive phenomenon, or it was not a periodic phenomenon, but it was still a wave, right? So you drop a small stone on a water body, okay, and you will see the ripples there coming out. So in sound wave, the disturbance is the height of the water, right? Both height and pressure. The height of the water, it gets disturbed. And that disturbance, the change in height, this is the information that travels to you if you are sitting on the bank from the center point where the stone was dropped, right? So this information is reaching you, and you are calling that it's a disturbance, which is the change in the height of the water that you are seeing by your eye, okay, seeing with your eye. But once the ripple stops, it will eventually, right, because of the damping, then it just goes away, right? So again, although it got carried on for a certain time, but then it stopped, right? So again, this is not a purely repetitive phenomenon, but you are calling it as a wave. It was repetitive only over a period of time, but you still call it a wave. A sudden sound, which just comes and stops, right? So that also generates a wave, but again, it's very short-lived. It's not periodic, right? So anything, any disturbance, be it periodic or not, can constitute a wave. And here by disturbance, I mean that there is a physical quantity which changes at some point of space, and that information reaches to you when you are standing at a different point in space, okay? So there are both types of variation involved here. One is the variation with respect to the spatial coordinates, which is x, y, z, and there's a variation with respect to the time coordinate, right? Okay, so now, given this, let's look at this phenomenon mathematically. Okay, so I'll argue that any physical quantity y that varies with space and time as the following equation, y equal to f of f of x plus minus vt, we will be able to call this as a wave. So f doesn't have to be a periodic function. It doesn't have to be a sine or cosine function. It can be just, e to the power x plus minus vt or something like that. Okay, or it can be any other function. It can be x plus minus vt square root. So it doesn't have to be periodic in nature. So the question is how this is traveling in space, because when I said wave, it is something that is traveling through the space, and this variation is the disturbance is reaching from one point to the other point. So now let's have a look at it from a mathematical point of view, or from a rather graphical point of view. So what I am saying is that, so this is lecture 1. So first consider the function f of x minus vt, okay? So suppose I'm plotting y as a function of time. So here I'm plotting y equal to f of x minus vt, and on the horizontal axis I'm plotting x, the spatial coordinates. And suppose the function has an arbitrary shape, which probably looks like this. So this is where suppose you dropped the stone, or you held your tuning fork while making the sound, or while generating the wave, okay, or in general generating the disturbance. Let's say this was the situation at t equal to 0, okay? So I am not assigning any particular name to this quantity, okay? I'll just assert that this quantity is a constant, okay? So now my question to you is, what happens to this function? Okay, if this was the function at t equal to 0, meaning that if this was f of x minus 0 into t, which is nothing but fx, right? So this was fx. Then how the function will look like at a later time, let's say t equal to 1 second. What will happen? Anyone? Don't type it in the chat box. I am not able to see it. Please speak up.
It would be shifted.
Yeah.
Right shift.
Right. It will be shifted towards the positive x-axis, right? So the probably at t equal to 1, this will be the shape of the function, and this is nothing but f of x minus v. Okay. So this is at t equal to 1 second. And again, at t equal to 2 seconds, it will look like this, right? So this is f of x minus 2v. This is at t equal to 2.
Sir, we are representing time on the x-axis.
No, we are representing x, the spatial coordinate. But I am varying this time as a parameter, right? At t equal to 0, what was the function? So this is still a coordinate in x, right? So because this is f of x minus v. So basically this is x equal to v. This point is x equal to 2v. so on and so forth, right? Initially, it was centered about t equal to x equal to 0, but as time goes on, the function will be x minus v, x minus 2v, so on and so forth. So it will shift towards the positive x-axis, and the center of the function will become x equal to v, 2v, 3v, so on and so forth. Clear?
Yes, sir.
Okay. So now the question is, what is happening here? As the time progresses, you can see that there was a disturbance or a quantity y. Okay. So initially, the situation was like this. You created some disturbance at x equal to 0, right? And this was at t equal to 0. And then, as the time is passing, and everywhere else y was equal to 0, right? In here, y was equal to 0. Only y was non-zero, or you created a disturbance, you created a change in y only in this region of the space. But as the time progresses, the disturbance, it travels to x equal to v. Then the disturbance travels to x equal to 2v, so on and so forth, right? So that means that as the time is progressing, this information that there has been a change in a physical quantity y, it moves forward along the x coordinate, okay? So that means that f of x minus vt, a function like this, it represents a wave which is traveling forward, traveling along plus x-axis as time progresses. You can do a similar thing with the quantity f of x plus vt. Okay, so here, as the time progresses, this quantity, it was initially at x equal to 0, then at t equal to 1, it will be shifted to x equal to minus v, then at t equal to 2, it will be shifted to x equal to minus 2v. So here, in case of f of x plus vt, as the time progresses, the disturbance will shift towards the negative x-axis. That means that f of x plus vt, this represents a wave traveling along minus x direction. Okay. So again, I would stress that this doesn't have to be a periodic function. Okay. So is this clear? Any question, any doubt, you can ask. Okay, so now let's try to give a meaning to the constant v that we are talking about, right? So what does this represent? You see, in unit time, in 1 second, how much was the displacement of the wave? How much distance did the wave travel in 1 second?
V.
Yeah, it traveled from x equal to 0 to x equal to v. So then what does v represent?
Speed of the wave.
Yeah, it represents the speed of the wave, right? So this constant v, now we know that this will represent the speed of the wave. So you see any function of this form, f of x plus minus vt, immediately you should be able to identify that this v is the velocity of the wave, and depending on whether the plus and minus sign, the wave is traveling forward along x or along the reverse x-axis. All right. So now I'll do some simple calculation, and from this mathematical notion that f of x plus minus vt represents a wave, and I'll show you that this can give rise to the one-dimensional wave equation. Okay, you will read about three-dimensional wave equation later on in this course. But to give you some flavor of how we can obtain the one-dimensional wave equation for this, let's proceed. Okay, so I'll take f of x minus vt, but you can, for the general purpose, you can take any of them and proceed with the derivation as I'm doing. Okay, it will give you the same differential equation. So I want to set up a differential equation, or rather a partial differential equation, because here you see that there are two variables, x and t. A wave must depend on both the spatial and the time coordinate. Okay, so the question is, what is the partial differential equation that this particular family of function satisfies? Okay, so let's proceed. So first I'll do the very simple thing. I'll differentiate this function with respect to x, and then I'll differentiate this function with respect to t. Okay, and then I'll try to come up with a relationship between these two differentials. So first, differentiate with respect to x. Okay, so I'm trying to obtain this. And you know that you can apply the chain rule. So f of x minus vt, here it will be dou of x minus vt, and then here it's dou of x minus vt, dou of x, right? So let's call this quantity over here as f prime. Okay, and how much is the second term? This is simply 1. So this gives me f prime. So what happens if I double differentiate it with respect to x? Right. So then,
could you repeat from first step?
Sorry.
Could you repeat from first step? Differentiate with respect to x from there.
Yeah. So I'm differentiating it with respect to x, right? So then you have to apply chain rule here. So I'm just applying chain rule. Okay. So now the first quantity I'm representing it by f prime. F prime is equal to this, and the second quantity is 1. It's a partial differentiation, right?
Yes, sir.
So when I differentiate it once again, then what happens? Then you get dou f prime dou x2, right? Meaning that, sorry, it's dou f prime dou x. So then what you get here is, again, I'll apply the chain rule, dou f prime by dou of x, because f prime is a function of x minus vt. So this is x minus vt, and here you have dou x minus vt dou x. So again, here you will get f double prime, and here you will get 1. So that boils down to f double prime. So let's call this equation that dou f dou x square equal to f double prime. So let's call this as equation 1. Okay, and now let's repeat the same exercise with respect to the time coordinate. We'll differentiate the function f twice with respect to time. Okay, so then how much is your dou f dou t? Again, this will be dou, just let me write explicitly that this is a function of x minus vt. Okay, so this is dou of x minus vt. Again, I am doing the chain rule, so dou of x minus vt dou t here. So now how much is this? Again, this quantity we already denoted it as f prime, and here's the second term, but here now the result of the partial differentiation is minus v. Okay, so you are getting minus v into f prime. So again, let's perform the second differentiation with respect to t. So v is a constant, goes out, dou of f prime dou t, and this is nothing but equal to, again, dou of f prime is a function of x minus vt. I'll just write it explicitly, and then dou of x minus vt, and then you have dou of x minus vt and dou t. So again, minus v, this is nothing but f prime, and here again you get another minus v. So if you had plus x over here, plus v over here, then you would have gotten plus v as a result of these partial differentiations. So you have nothing but v square f prime. Okay, f double prime. In other words, 1 by v squared dou to f dou t squared, that's equal to f double prime. And let's call this as equation number 2. Okay, so now compare 1 with 2. So you have f double prime on the RHS of both the equations. So you end up with a relation, which is the very famous one-dimensional wave equation. That's dou to f square is equal to 1 by v square dou to f dou t square. So this is the kind of general differential equation, okay, that a wave has to satisfy. If the wave is propagating in 1D, if the wave is propagating in 2D, then there is corresponding generalization of this, which is the 2D wave equation, and then there is 3D wave equation. Okay, so you are going to study all of these, but a little bit later when we pick up the topic of electromagnetic waves. Okay, but to give you just a very basic idea of what a wave is, what does it mean physically, what is its relation with the maths, okay, how a simple function can represent a wave, and then from that ab initio, what is the scalar wave equation that this quantity must satisfy. So now you may ask why I'm saying that it's a scalar wave. I'm calling it a scalar wave because the quantity y, I assumed from the very beginning that it's a scalar quantity, okay? But it doesn't have to be like that, okay? It doesn't have to be that way. The quantity y, it can be a vector as well, because I said that any physical quantity can constitute a wave. Any disturbance in any physical quantity, be it a vector, be it a scalar, it can be a wave. Okay, so since I assume that y is a scalar quantity, I am calling this as a scalar wave equation. But you will see that when it comes to the electromagnetics, there are two fields involved. One is the electric field and one is the magnetic field. And you know that both of these quantities, they're just vector quantities. So you will get something what is known as the vector wave equation. Okay, but to be able to solve the vector wave equation, we will adapt some ways to convert it to the scalar wave equation, probably by splitting it up into 3 components and consider each of the component, the x component as a scalar, the y component as a scalar, and the z component as a scalar. Okay, but there can be 2 types of wave equation. One is scalar wave equation, the other one is vector wave equation. All right, so again, questions, please go ahead if you have any. So yeah, so in short, just before I take up the questions, so you can easily understand it through the shift of coordinate, and you can calculate the rate at which the quantity y shifts along x plus x or minus x direction, and that's nothing but v, as I have shown you. So that's why this constant appearing over here is the velocity of the wave. Okay. All right, so if you have any question. Any doubt? Look, the main thing is that you understand the phenomenon very clearly, okay, from the physical point of view, and then we'll go to the maths.
Sir, what is the significance of the equation that we just derived?
Yeah, so the significance is that suppose you were given a particular situation, okay, so where there are certain boundary conditions, you know that you can solve a differential equation only by only when the boundary conditions are properly specified, right? Otherwise, you can solve a differential equation, right? So instead of calling this quantity f as a very generic quantity, there are many simplifications that's possible under certain situations. Okay, so you can actually give meaning to this function. It can be a sine function, it can be a cosine function, it can be a combination of both of these. Okay, so the question is, what equation do you need to solve when you want to see the particular form of the function, when you are interested in a specific form of this f, whether it's a sine or cosine or a combination of both or something else. Okay, so then you should be able to solve some particular type of equation, right? So that's the first significance, that you start with this wave equation, you apply the boundary condition, and you get the final solution. And you will see that the solution is, of course, of the form of f of x plus minus vt, because we started with that. We obtained this differential equation based on our assumption that it has to be of the form f of x plus minus vt. But then it becomes more physically relevant for practical purposes to know what this particular function f is going to be. Is it going to be a sine function? Is it going to be a cosine? Is it going to be a combination? Is it going to be a superposition of many sines, many cosines? What is it, right? So under that situation, you start with the wave equation and you solve for it. Okay?
Oh, okay, sir. Okay, fine.
So there's a second significance of these two. The second significance is that, and you will see in electromagnetics, that we will form something which is known as the Maxwell's equation first. Okay? But it won't be apparently clear at the very outset, when even after I have obtained the Maxwell's equation, that whether you can call such a set of equations or any quantity which is satisfying such a set of equations as a wave or not. Okay, so I'll show you that you combine the Maxwell's equation in different ways, and what you get as the simplified form is the wave equation. And then I can say for sure that the electric field and magnetic field, they are waves. Okay, but just from looking at Maxwell's equation, the four Maxwell's equation, they're very famous. Just looking at them, it's not possible for you to tell that it's a wave. But then you do certain mathematical manipulations, very simple mathematical manipulations, and you can immediately show that it will be cast into a form which looks like the wave equation, or rather, which is the wave equation in 3D. And then you immediately infer from there that yes, electric and magnetic field, they are wave indeed, which was not possible for you just by looking at Maxwell's equation. So this is the second significance. Sometimes just by looking at a quantity, or just by looking at some other equation that the quantity satisfies, it's not possible to infer whether it's a wave or not. But if a quantity, if you can show that a quantity satisfies the wave equation, then you can be 200% sure that, yeah, it's going to be a wave. Okay?
Okay, sir. Okay, fine.
All right, so any other question? Yeah, so the scalar quantity in the equation, right? So I assumed that this quantity y is a scalar quantity, like the height of the water level. Okay, so that's why it's a scalar wave equation. But there can be a situation, for example, in case of electromagnetic wave, both electric and magnetic field, they are vectors, right? So there is something which is the vector wave equation, and so it's very similar to the scalar wave equation, but the only difference is that the f is replaced by a vector quantity. Okay. So in that case, we will end up in a situation which is known as the vector wave equation. So you will see how a vector wave equation looks like when we discuss the electromagnetic wave equations later in this course. But it's good to know from the very outset that not only a scalar quantity can constitute a wave, but the vector quantities like the electric field and the magnetic field, they also constitute wave.
So could you explain that why are we considering y as a scalar quantity?
Well, I mean, this is just from the simplification point of view. Like if I give you a vector quantity at the very outset, I'm saying that, okay, fine, here's a vector and here's the vector wave equation, it becomes much more difficult for you to understand. Okay, so I'll just give you a glimpse that how a vector wave equation will look like. This will probably look like something like this. Okay, this will be the vector wave equation in one dimension. So this quantity f can be a vector quantity as well. Okay, this can be electric field, magnetic field here, or here this can be just the height of the water level that's varying.
Okay, sir.
Okay. All right, so now I'm going to ask you a few questions. So you see, the gravitation is very strong force, right? You have all studied the Newton's law of gravitation, and you have also studied Coulomb's law, right, for electrostatics in your class 2. So the question is, which force do you think is stronger, the gravitation or the electrostatic force? What's your opinion on that? Anyone? So Arjun, any reason for your answer? You can just speak up, So you are correct that the electrostatic force is going to be, but doesn't it surprise you that the Earth is rotating at such a high speed, and or the Earth is pulling you with a very okay, great. So the Earth is pulling you with such a strength that you are not flying off because of the acceleration which is being imparted to you by the Earth. You are in the same rotating frame as the Earth is, right? So you should feel a pseudo force, which is the centrifugal force, and you should be just thrown away off the Earth. But the gravitation is so strong that it's holding all the objects, the mountains, the buildings, the people, so many plantations and vegetations. They are just on the surface of the Earth. They are just not flying off, So it may look like that, it's the gravitation force is very strong. But I'm going to give you, again, from both the physical viewpoint and the mathematical viewpoint, that how strong the electrostatic force can be. Okay, so let's consider a physical example first. Okay, so can anyone tell me that why when you are standing on the ground and the Earth is pulling you towards the center, why you are not just just entering the ground and reaching the center of the Earth because of this huge pull? So what is preventing you from doing so? So what is the force which is counteracting gravity? If you are in
Centrifugal force.
no, it's not the centrifugal.
So the normal force.
Normal reaction.
But what is the origin of the normal force? That's what I want to understand here.
So we are also pulling Earth at the same force, the force the Earth is pulling us.
Well, I mean, that's true, right? But the question is, when I draw the free body diagram of yours, the force will appear on the Earth with which you are pulling the Earth. Okay. But since you are, there's normal reaction involved, right? So when I draw your free body diagram, there should be a force with which the Earth is pulling you, and there should be a normal force. The normal force is the balancing. That's what you know so far, right? But what is the origin of this normal force? It's not the force with which you are pulling the Earth. So the force with which you are pulling the Earth, that will appear in the Earth's free body diagram. Okay. So my question is specifically, what is the source of this normal force? Okay, so let me show you. So when you stand on the Earth, okay, so the ground was initially like this, and imagine that these are the layers of atoms or molecules that the Earth is constituted of. Okay, so it can be a very random arrangement. So it's of course not a very ordered arrangement like I'm drawing here. Okay, but just to give you a flavor that there are many layers of these atoms and molecules which are very closely spaced with one another. Okay, and you know that they can interact with each other through the electrostatic force, right? So what happens when you stand on this is the following. So the part on which you are standing, it actually deforms. Okay, so the molecules and atoms, they're just becoming like this. The next layer is probably deforming, but maybe a little lesser. And ultimately this deformation goes away as you go deeper into the surface of the Earth. So what is happening here? This distance was initially this without the deformation, but when you stood on it, the distance is this. So immediately the molecules, they will come closer to each other, and the charges within the molecule, the electrons on the outer orbit of the molecule, they will start repelling each other, right? So that means that they will try to repel. So you see that from each of these points of deformation, the electrostatic force is acting up and imparting a force on you. So now that's the origin of the normal reaction. It's the electrostatic force. When the two layers of the molecules of the earth, they are coming close to each other. So this is a very classical explanation. Okay. So you imagine that this earth is a whole big object which is pulling you, but your feet is so small in comparison to the size of the earth. But only these many molecules which are lying beneath the feet, okay, in the deformed area, they are sufficient to counteract the force of such a colossal thing, which is the earth. So you can imagine the scale difference between the gravity and the electrostatic force, and how strong electrostatic force is. Your feet is so small in comparison to the size of the earth, and you are still standing. Okay. All right. So now let's look at this problem from the maths. Okay. So we'll simply go back to the law of gravitation, and we'll simply go back to the law of Coulomb's law of electrostatics, and we will try to compare the relative amplitude of these forces, that how much they differ. So now you have an idea that electromagnetic force is very, very strong in comparison to gravity, but the question is how strong it is. Okay. So, right. Okay. So I'm going to consider 2 point masses, 1 kg each. They are separated by a distance of 1 meter. So you can easily calculate the gravitational force by the formula G m1 m2 by r square. Okay. And this is of the order of 10 to the power minus 11. Because your m1, m2, and r, all of them, they are just 1 SI unit, right? So you are only left with F grav equal to G, which is nothing but 6.67408 into 10 to the power minus 11 Newton meter square per kg square. Okay. All right. So now what happens when you have two, say two charges, and each of the charges, they are 1 coulomb, and again separated by the same distance of 1 meter. Okay. So when you do the maths and put in this constant 8.85 into 10 to the power minus 12 farad per meter, okay, and divide it by 4 pi, you will see that this comes out to be 10 to the power 12. Okay. So all this difference, so the gravitational force is the on the order of 10 to the power minus 11, and the electrostatic force is on the order of 10 to the power 12, right? And this huge scale difference is coming from the constants, the gravitational constant and the free space permittivity, right? And in one case, the constant is appearing in the numerator, and in the other case, the constant is appearing in the denominator. As such, there is not a huge scale difference in between the constants. They are just 1 order of magnitude higher than one another. G is 10 to the power minus 11, and permittivity is 10 to the power minus 12. So not much, just order of 1 order of magnitude, right? It's the fact that in one case the constant appears at the denominator, and in the other case it appears at the numerator. Okay, so when you do this Fe by Fg, then it comes out to be 10 to the power 23. So typically the electrostatic force, can you imagine it? It's greater than the gravitational force by an order of magnitude 10 to the power 23. Okay. So if you, so any question, or if you want to ask any doubt, anyone?
No, sir.
Okay, great. So now again, let me ask you the second question. I mean, you will be amazed to see this number. And something that I didn't tell you so far is that how can one not get interested in this subject? So when you look at the sky, right? Suppose you are looking at a distant star, If you are, of course, living outside Delhi and don't have the pollution, you don't see a lot of stars in Delhi nowadays. But if you are able to look at it, then just pause for once and just think about it. The light from the star which was emitted, right? The star is actually many light years away from you. The light takes it has to travel a great distance to reach you, and it takes a time by which probably the star has died. And no information can travel faster than light in this universe, right? So it's the fastest signal that you are receiving from the star, okay? And it's very possible that when the light has reached your eye, the star has actually died, okay? It's not actually there. What you are seeing the past, the last light that was emitted from the star. And still, one electron that was vibrating, or one charge that was vibrating in the star, or probably it was undergoing an oscillations many years back. And right now the star is not there. That signal is coming to you and making the charges inside your eye to oscillate so that you can receive that light signal. Right? So this is amazing. I mean, a signal which was generated way past, and the object itself probably is not there. It has died. It has been destroyed, or it has become a red giant or a white dwarf and whatnot. But you are able to still feel it by means of the same wave that makes one electron in your eye to vibrate, and that's how you receive the light signal. Let me just imagine how how amazing this is. Okay, so now I said that the electrons are vibrating. That's why you are receiving the signal. The electrons are vibrating. That's why the electromagnetic wave is being generated. Before going to the details of how this is happening, let's consider another question. We don't have much time left, I guess 10 minutes, so this is probably going to be the last topic. So how fast do you think an electron move? Suppose I give you a piece of conductor, okay, a conducting wire. So imagine that, imagine you are in your classroom, okay, in your lecture halls that you have not seen for a long time in IIIT. And there is one light at the end of the hall, and there is a switch right after you enter through the door of the hall, okay? And you switch on the switch, okay? Light gets switched on instantly. Okay, so does that mean that the electrons, they traveled instantly from the one end of the room to the other? Anyone?
No, sir.
Okay, it didn't, right? Because as I said, that no information can move faster than light. So it must have taken a finite amount of time. Okay. So now I ask you that, then how fast does an electron move? Any idea? Do you know how fast the light moves? What is the velocity, or what is the speed of light?
3 into 10 to the power 8 meter per second.
Yeah, 3 into 10 to the power 8 meter per second. So can you tell me how fast an electron moves?
So the drift velocity of the electron inside a conductor is pretty slow than that, 3 lakh kilometers per second.
How slow? How much? Any idea? Just give me, throw some numbers so that I can appreciate what you are saying. Okay.
Maybe 10 to the power 6.
In meters
10
per
to the power
second, I
6
think.
meter per second?
Yeah.
Okay. Oh, that's close enough. It's actually of the order of 10 to the power 5 meter per second. Okay. That's how fast an electron is moving inside a conductor. Right? But there's a catch to it. The catch is that it depends on what length scale you are interested in. Okay? So the electrons, they only move on an average of few tenths of nanometer. 1 nanometer is 10 to the power minus 9 meter. Only few tenths of nanometer, meaning that 10 to the power minus 8 meter on an average inside a conductor. And after traveling this average distance, it gets scattered from the other molecules in the lattice, in the solid, okay, or in the conductor. So this is what is known as the mean free path of electron. So it's not that when you are switching on the light, the electrons are traveling at a speed of 10 to the power 5 meter per second from your switch to the light bulb. Okay, it's not happening because it will only travel a few nanometer, tens of nanometer, before colliding with the next molecule. All right. So
Yes, sir.
then the electron, it takes a very zigzag path to reach from your switch to the light at the other end of the room. Okay. So consider the electron was free to move with a velocity of 10 to the power 5 meter per second. Okay. So given that the circumference of Earth is 40,000 kilometers, the equatorial circumference, okay, the electron would circle the Earth in less than 7 minutes. Okay. But then the question is, in a conductor, there are many scatterings that are happening, which is slowing the electron down effectively. The effective speed of the electron is going to be much slower when you apply the electric field, and that velocity is known as the drift velocity of the electron. Okay. So if you are interested in a larger length scale, which is many order greater than the length scale of the mean free path, which is 10 to the power minus 8 meter, then you have to consider this effective velocity of the electron. And it turns out that the electrons, it can travel in a conductor only few millimeter in 1 second. Okay, so a few meter in about 15 minutes. Now your room is, 8 meter, 9 meter, 10 meter. So imagine how much time the electron would take from your switch to reach the light bulb. Okay, it will be 15 into 2 into 3 into 4. It depends on the size of the room, right? But at least, assuming that your room is about 8 meter, or the distance between your switch and the light bulb is 8 meter, then it will be 120 minutes, like 2 hours. So you switch on the light, you wait for 2 hours, and then you see, oh, fine, my light bulb is now lit up. But you don't see that. So what's that reason that you don't see that, even though the electrons are moving so slow? Anyone?
Wave is propagating.
Well,
So-
forget about wave now. Okay. Even if the wave is propagating, of course, it's not propagating at a at a speed such that it will reach from your. You are correct. A wave will be propagating, but it's not so slow that it will reach from your switch to the light bulb in 2 hours. You don't wait for 2 hours. You just wait for less than a second for your light bulb to switch down.
So there's not a single electron in the entire.
Exactly. There's not a single electron that is flowing. There are still few electrons which are running here and there randomly near to the light bulb, right? So so it's an average behavior that is taking place. So you switch on your light, and then there is one electron. As soon as the field is set up, there is one electron which is just adjacent to the light bulb, is pushed to the light bulb, and the filament just gets lit up, right? So it's not the electron from the switch is flowing to the bulb, which is giving rise to the light, or which is switching on the appliance. It's the electron which is adjacent to the appliance, which just entered the filament, heat it up, and you see light. Okay, so even though the electron which is right at the switch takes 2 hours, the electron which is adjacent to the appliance only takes probably no time to reach the appliance. Okay. You see all these little details, they're very fascinating. And anyway, so yeah, do I have more time today? No, I already crossed. I'm sorry. So yeah, so we'll end up the lecture here, and we will start at this point, that how accelerated charge can make waves. Okay. What kind of disturbance do you see in the electromagnetic field? So anyways, thank you. If you have any question, please email me. If office hour needs to be set up, I'll do that. If I can answer your question over the email, I'll do that. Okay. Thank you very much.
Thank you, sir.
Sir, will there be office hours for the TA?
Yeah, there will be office hours for the TA, but this being an online setting, you can just email the TAs and they will set up an office hours according to the mutual convenience.
Thank you, sir.
Yeah, you are welcome. Okay, thanks everyone. Bye. See you on Thursday.